Thank you, Carl, and thank you for the invitation. It's a pleasure to be there, even if I'm not really part of this community. What I think my talk is probably not unexpected science, if I have the understanding of science in this community, but it's probably an unexpected talk for you. What I want to present is what we have done over the last 5 years to productionize a multi-parameter waveform inversion of low-frequency, wide-aperture active data. What here it is important to notice is that I'm staying acoustic, which seems to be very weird. But I will try to explain why. So the first introduction, I think most of you know, is that why we are doing that is that, okay, we need to provide relevant Earth information for reservoir exploration and production. And for that, basically, we need to understand the first 10 kilometers of the subsurface, how it will react if we produce a reservoir. So we need to do detection, characterization, monitoring, but we also need to understand the geohazard and what's happened if you produce or inject. For that, we need to basically to provide, of course, the first thing we provide is a 3D structural map, but we would like to go further, and it's also to have information on rock property, fluid content, but also on stress regime. Of course, in the industry, we are not using only seismic data. We are using the full range of geophysical data from gravity to electromagnetic. However, the seismic data, the active seismic data, are the main approach because of the localization of the wave equation. It gives us information on where the events are. And mainly we are using P-wave. There are a strong reason why we are using P-wave is because the way we acquire the data and the cost we put in the data means that there's a limited recording time and the frequency band. This is a P-wave who give us information on the deep structure, what I mean deep, 5 to 10 kilometer deep. And what we do is that we use reflected events recording in time. We try to map them back in depth. For that, we need to have which we call a background velocity. And then after that, we try to interpret the amplitude of the reflection. For that, what we do generally, we pick attribute in the data and we invert this attribute. Of course, the question comes, and I think it has also been mentioned earlier during this workshop, is that can we get more from the seismic data? And of course, everyone thinks, okay, yes, please use the waveform, or I should say the wave field. And that has been proposed in the 80s, and in fact, the oil industry is working on that since the 80s. However, we did not have a great success for productionize, and I will explain why. The method is simple. It is just a data fitting. Okay, after that you can choose the norm that you want, and I will not discuss that, but okay, you have an approach where you are able to model the experience, and you try to find a model that explains your experience. I mean a model, which is, we would like probably to go further than that, but we can't for the moment. Like any geophysical problem, the inverse problem is ill-posed. And another issue with a wave equation, and that is because of the localization of the wave equation, someone would say is because of the second derivative in the wave equation, is that we have a data misfit which is all oscillatory. And there are two main reasons why our data misfit is oscillatory. The first one is that our wavelength has side lobe. And also if you are alpha wavelength off, you will match the wrong lobe between your synthetic and your observed data. But there are more, a second issue is the event identification. I think in seismology we basically pick the events and after that windows the trace. Here we try not to pick the events, so we have to find a way that my synthetic and my observed data, when I match them, they match the correct events, and that is it's a big issue. Unfortunately, the model is too expensive, and from a mathematical point of view, if you have a oscillatory function, you would like to use a stochastic approach. Unfortunately, we cannot do that. It's too expensive to model the wave equation. So we rely on local optimization. That means that we have to understand what's happened when we use the gradient, the search direction, if you want, or that, when we use that to slowly update the model. And the second thing is that we have to keep in mind that we are dependent on the initial model. And that's very important when we interpret. Okay, you would have all noticed that, I'm sorry, I will not do any interpretation. My talk is more on methodology. And so, okay, computing the gradient is not an issue. The adjoint state method is there since the 70s, and so we know how to use it. The thing I want to show you next is what is a gradient. And so I took two examples. One is when you have a transmitted wave, one is when you have a reflected wave. The transmitted wave clearly is when you have a smooth background which increases in depth. Obviously, okay, the map has something strange. Here I assume a streamer data set or a streamer data set and surface data set. And as I say, I focus on the acoustic wave. That means that on this one, I mainly focus on this diving wave. And if I compute what you call the sensitivity kernel, we call it gradient when we start the sensitivity kernel because we have far more a receiver. What we see is that we see something which is relatively smooth. And the most important thing here to understand is that, in fact, when I compare my observed data and I compare with my synthetic data, I basically see geometrical effect. That means that my cost function depends on kinematic parameters. And since my model is smooth, my acoustic assumption is a fair assumption. I don't have converted waves. So this one is a nice case. Let's say the fact that we have an oscillatory function. I will come back to that. The reflected case is far more complicated for full waveform inversion. In this picture, here you have the reflection on this layer. Here, when I compute the gradient, the sensitivity kernel, I assume that I perfectly know the first layer. And we know that the gradient is a zero-lag correlation between the incident and the backpropagated field. And when you compute the sensitivity kernel, of course, you obtain the diffraction curve that when you stack will give you the location of your interface if your velocity is not too far. But what you also see is that you have a correlation along the wave path. And this correlation is not due to a kinematic error in the media that you propagate through. Is due to an error in the reflection coefficient in your model because you don't know the Earth below this first layer. And unfortunately, since you are using a gradient method, the gradient is this one. And imagine that you have this initial model and you have this gradient, and the goal is to obtain the velocity here. You see that what is the problem with the local optimization method when we have reflection wave. And it's a crucial point to remember when we use full waveform inversion with surface data is because we may be able to create a lot of artifacts of our model which look like high resolution image. So in the industry, basically, we know that, or we hope that, or we try to deal with that. And with reflection, mostly what we do is that we use so-called migration velocity analysis technique or travel time inversion technique. That means that we don't use the criteria, the classical least square criteria. We use another one to try to find the kinematics. And then after that, if you use something close to the Born approximation, a linearization of the equation, of the wave equation, what you obtain is that, okay, you are able to obtain the relative impedance. What we call that migration or least square migration in our industry, in our exploration geophysics. But now what do you do if you want with full waveform inversion to retrieve some of the long to intermediate wavelengths? In fact, the best approach, if I look at my gradients, is to rely on a wide aperture long offset data. And we were quite fortunate over the last 5-10 years is that a new development in acquisition were a key enabler for this technique because we are now acquiring long offset and also we are acquiring wide aperture, of course, because we are working 3D, and also we are acquiring a lot of low frequency, or at least we have moved from the 6-7 Hertz frequency down to the 1 to 2 Hertz frequency. And that is the key enabler for these techniques. It's not the methodology by itself, but is the availability of a new data set. Of course, as I say, we rely on the acoustic modeling because of the cost efficiency. And for that, we know that the reflectivity is the issue I show you with the gradient. In fact, the dynamic of the interface is elastic. So with the acoustic, we will have to mitigate this issue. And the low frequency are crucial because the cost function is oscillatory, and with the low frequency we know that the oscillations are inversely proportional to the frequency. So if you start with a low frequency, you have more chance to be in the global valley and then to move slowly to the higher frequency in order to get a bit of resolution. Now when you do an inverse problem, when you know that you can dream of a lot of parameters, you have to question yourself is how do I parameterize my inverse problem? And since it's a nonlinear inversion, the parameterization plays a non-negligible role. The strange thing enough is that, as I say, is that we are using acoustic media. But since we have a long offset, we know that the Earth is anisotropic. So we have invented in exploration geophysics an equation which we call that anisotropic acoustic by just zeroing the shear modulus in the Hooke's tensor. Well, that's not a physical equation, okay, but it serves purpose for us. And now we have to understand how to parameterize my inversion. And basically what we choose, at least in Shell, is that we choose that we will play with two kinematic or geometrical parameters, basically two velocity if you want. Okay, well, we don't do with two velocity. We use the NMO velocity, which is something close to the vertical velocity, except that when we have anisotropy, we don't have depth control, and it is called the NMO velocity. The NMO velocity replaces, in this case, the vertical P velocity. And also, we don't invert for both vertical velocity and horizontal velocity, but we also use the ratio between the horizontal and the vertical velocity. The reason is that we believe that we can put a larger smoothing on the ratios than on the velocities. Thanks to that, we reduce the null space of the problem. And to mitigate the issue at the interface, we have to use what I would call a local dynamic parameter, and one we have in the equation is the density. We don't retrieve the density. We just use it to mitigate the effect, and in fact we can call that a pseudo-density. When I look at this parameter, I want see that, okay, I have trade-offs. At short offset, the reflection data, I have a trade-off between the NMO velocity and the density. We know that our data is sensitive to the impedance, which is the ratio, the product of the two. At long offset, my data, this is the transmitted wave, are more sensitive to the horizontal velocity, and of course the horizontal velocity is the product of the NMO velocity and its ratio. So I have an issue here which creates some difficulties. And then after that, okay, as I mentioned, we need to do multi-scale approach, so we work from the low frequency to the high frequency. As I mentioned earlier, nowadays, and in the example I will show you, the two examples I show you, basically to retrieve the background velocity, we invert frequency between 1.5 to 6 Hz. About that, and we try to focus on the long offset. So let's move to the first example. The first example is an example from offshore West Africa, where we have carry out what we call an OBS or OBN in the industry nowadays, ocean bottom nodes survey. Here, so you lay down about 1,000 nodes on a grid of 400 by 400 meter. This corresponds to the blue dot in the pictures, and you shoot over it. In this case, we shoot about 300,000 shot on a grid of 50 by 50 meter. In this case, we have 1 kilometer of water. So basically, we cover 400 square meter with this kind of data. The first thing we do is we need to do processing of the data. Even if, because the nodes are on the seafloor, we have a relatively quiet environment compared to when we acquire streamer data, we still have swell noise, we have this effect that we have to process out, and we do it. I don't have the time to discuss more on what we do. But now we want to qualify our model. So one way to qualify our model is to use the data. And so since we try to invert or to retrieve the background with a long offset, we can use the short offset to try to validate the data. And here we are in a luxurious position because we have a very huge data, is what I mean. We are speaking of billions of traces. What we do is that we know that the Earth, each point of the subsurface, is seen through different incident angles. So if I use the migration and if I migrate the reflected events that I have recorded in time, if I migrate in depth, they should all arrive at the same depth if my velocity model is correct. So if my velocity is correct, my CIJ, my common image gather, should be flat. So here is the result that we had when we used the initial model. It was not too bad. And then we did a velocity-only full waveform inversion by putting a contrast at the seafloor between 1 to 2 for the density, and no shear contrast, of course. And what we end up is that the gather were no longer flat, which means that even if we were improving the fit of the data, we did not get a correct velocity model. And the reason is because we were over-interpreting the data with one parameter. That means that we were putting a lot of lobes at the seafloor to try to cope with the amplitude behavior of our data. To compensate for that, what we do is that we invert for both density and velocity, and in this case, as you can see here, we have improved the gather, and thanks to that, we have stabilized the inversion. It is just a mitigation, but it's very useful for production. The second thing is that we noticed is that, okay, what I mean, here the maximum offset were probably between around 12, 13 kilometers, and in this case we needed to take into account the fact that the horizontal and the vertical velocity was not the same. We could have some idea of the initial values, but they were not enough to give the best result, and so what we did is that, okay, in this case we inverted also for the so-called eta parameters, the ratio between the two velocity, and indeed we improved the result. We are not yet ready to interpret this velocity ratio, because in fact here we assume that we have a vertical transverse isotropic Earth, but it is probably not the case, and in this parameter we put probably more than what should be in. So if I summarize what the result that we obtain is that, okay, I just show you one slide. So on the initial model, this part where we don't have a lot of velocity anomalies, wavelength scale of velocity anomalies, our ray-based method works perfectly well. And as we can see, we have on the background we have the velocity model, the background velocity model, and in the foreground we have the reflective, the migration of the data. And on my common image gather, I see that I have a flat common image gather. But it's in zone, we see that we don't have focalization of the event in this region. And the reason is because we have difficulty to image or to find the velocity in this region. When we carry out the full waveform inversion, we have a nice recovery of the anomaly or the velocity variation at the wavelength scale in this region, which allow us to refocus the energy deeper. And okay, this one was attributed to gas, and this one to hydrates. What we see here is that the full waveform inversion were enabling us to retrieve wavelength scale variation in the velocity model that we had a lot of difficulty to find with array methods. Okay, that's basically what, there is one point that I should mention is that since we are using the diving waves, we don't have a very deep penetration because the wave, since we record only on 12 kilometers, the diving wave we record does not penetrate very deep. Basically, a rule of thumb says that we basically scan the Earth with this method up to about 1/4 to 1/3 of the maximum offset. So this will not solve all our problem. The second example I want to touch on is the land. It's a land example, and here it is a survey that are carried out in Oman, so I take a part of it, and I will show you some of the result. So here it's a 30 by 10 kilometer. But let's first discuss about the acquisition. As I mentioned, we wanted to record between 1.5 to 8, well, basically 1.5 to 86 Earth. But we wanted to do that in a cost-efficient manner. And the current acquisition in Oman takes years. So we cannot multiply by 3, 4, 5 the acquisition time. To do that, people come up with a number of solutions. One is simultaneous shorting, and the other one was to try to figure out how to have an efficient acquisition for the low frequency without increasing too much the recording time, and for that we use a nonlinear sweep. Here I should mention that even if we record 1.5 Hz, or we try to use 1.5 Hz, we still use a 10 Hz geophone. The way that we lay down is a typical land example is that you have a number of receiver line. Here the line are separated by 250 meters, and we have one receiver every 25 meters on each line, and you have that for about 12 kilometers. On the central one, you use your vibrator and you shoot on this one on a grid of 50 by 50, and then you move the line, which is the further one, you move it on the top and you continue. With that, we end up with data that is about 12 kilometers inline offset, both sides, and 6 kilometers cross-line offset, which means that we end up for just the 300 kilometers square, we end up with 40 terabyte of data, which correspond to about 6 billion traces, if you want, and that means that we have 52,000 receiver, which is about 125,000 shots. We will not invert for all receiver position. Of course, we always use reciprocity in this case, but we do need that for signal processing. And so here it's raw data. And on this raw data, you see several things. First, obviously, you see the ground hole. On land, it is the main event. And since we are acoustic, we need to remove that. But we also see other type of ground hole here. And in fact, as the activity during the acquisition, for instance, a moving vehicle. We can't see vehicle moving during our acquisition. We need to get rid of all that. And we take the fact that we have many traces and relatively well sampled by resorting the data correctly and by using appropriate processing, which is not only a CMT base, we are able to process out the noise, what we call noise in this case, and to find out to get this process data. Here we still have a strong event which corresponds to the engine noise of the vibrator. And then, since here I mentioned here I will invert from 1.5 to 6 Hz, I show you a panel with an eye cut at 3 Hz. So even with this eye geophone, 10 Hz geophone, we get nice data between 1.5 to 10 Hz. And in this case, what we do here, I'll plot you, it's a stack over 8 receivers. So we stack with an array of 400 meters, if you want. But it's not a pure direct stack, there is some travel time correction. Of course, in this case, I don't want to invert the reflectivity with the problem we have, and so we blank out. Yeah, we blank out. Of course, there is a bit more taper than what I show it, and we focus on the diving very long offset. And the result we obtain is this kind of things. Is that here we have an initial velocity model because we have a nearby well, so you take the velocity, and after that you create your 1D model. You have an idea of the layering of your Earth. That means that we know that we encounter shells and carbonate, and we generally have more anisotropy in the shell, so we put a bit of anisotropy in the shell. And in this case, we do a simultaneous inversion of the two kinematic parameters. And here you have the big Mahari fault. And then when we end up after a full waveform inversion, that means that we progressively increase the frequency content up to 6 Hz, and we have carried out, I think, roughly 125 iteration. And you see that we have improved quite a lot the imaging in this part of the fault. We have also the velocity, which now we conform more with the layering. You please notice is that the velocity variation that we have is around 1,000 meter per second, which is 25 to 30% variation. Variation is quite a large variation if you think about the fact that we are nonlinear. And if you look more carefully here, you will also see that we have velocity variation around the small fault. So just for for conclusions, what I show here is that I show that by using a non-physical wave equation, which is an isotropic acoustic wave equation, we have been able to productionize the full waveform inversion, and now it's a common is run every day in the oil industry. But we needed to do multi-parameter inversion. The multi-parameter is still a challenge, and the key enabler in this approach is the acquisition. We are able to do that because we have better data. We have better data on land and on sea. And there is a lot of work going on in the acquisition currently. I did not mention what we are doing currently in research. I will just put a few issues that we have, despite the fact of the multi-parameter. One challenge that we have is definitely the fact that we have difficulty to handle very large variation. When, for instance, we move by 3,000 or 4,000 of meter. In the Gulf, for instance, we plug the salt, and full waveform inversion is not will not allow us to retrieve the salt. And of course, here you can say, okay, my acoustic assumption is no longer valid, and it's probably true. And the other thing is that maybe you would be disappointed by the image that I show you, because what you would like to get is not a background velocity model, and then after that use a reflective migration to get. You would like to retrieve the Earth parameter with a nice resolution up to 40 Hertz. And for that, we are not able to do that currently, except on small cases where the shear variation are weak. But when we have a large one, we are not able to do that, at least in production. And one of the reasons is obviously the cost of the elastic method. I will skip this, and I want first to thank Shell to allow me to make this presentation, and also our partners will allow us to show the data. But I also want to mention is that in order to do that in a production matter, it's basically three groups who work together. We have the acquisition group who have provided us data which allow us to use this algorithm, and we discuss with them to know how to acquire efficiently the data. The second one is obviously the image, what in our industry we call the imaging group, which will basically be the numerical physicists and coding. And the other one is definitely also the processing. We have dedicated package to process correctly the data. Thanks a lot for your attention.
We have time for a quick question or two as we transition.
Yes, we do. But if you think that the strength of the surface wave is maybe one order of magnitude larger than the strength of the diving wave we want to look at. If we do it brute force, it will never work. So the idea is to first to interpret the diving wave, either with the classical model methods, or after that with full waveform. And then when we have a correct estimation of the diving wave in our model, to account for. There is a big issue here with the surface wave to interpret it. We probably will have a model of the resolution of 1 meter to 2 meters. I cannot discretize my Earth up to 10 kilometers deep at 1 meter. So there is a computational challenge here, or a numerical challenge, is how to incorporate a very precise near surface when we do I would not say a deep, but when we try to image the 5-10 kilometers. And I think you have about the same between the crust and when you image a mantle.
Yeah, in your initial slide, you mentioned something about trying to find something about the stress regime. Would you comment a little bit more on that, please?
Yeah. What we try is to do. So the way we do that is that we use the velocity to try to find the pressure, pore pressure, and that we would like to go further on that, and also to use anisotropic parameter to find, or even absorption to find the different stress, which is basically would correspond to faulting. It is not yet there. It is not yet there, but we would like to be able to provide that with our seismic data. And here, of course, I use only P waves, and I use only a vertical displacement. We may need to move to a more multi-component data set.
All right, please track Renee down at the coffee break if you have more questions, and well, let's thank our speaker one more time.